Hi, my name is Américo Cunha. I'm from Rio de Janeiro State University, and I will present this work entitled An Embedded Discrepancy Operator to Improve Epidemic Compartmental Models Prediction. This is done in collaboration with Professor Rebecca Elizabeth Morrison from University of Colorado Boulder. Well, epidemics are in fashion, and the great public is now very concerned with this because of COVID-19, but definitely this is not a disease in the world which causes concern. Recently, in recent years, Zika fever was a disease that caused a lot of apprehension in the international community. Okay, Zika is a disease caused by a aviviride virus called the Zika virus. It was first isolated in Africa, in Uganda, Africa, in 1947. Okay, and its main vector is the family of mosquitoes of Aedes type. Okay, especially here in Brazil, in recent years, Zika received a lot of attention because since 2015, we have here more than 140,000 cases reported. Okay, Zika itself is not a serious disease by the symptoms and by the symptoms of the disease, but the main concern is because of the consequence that this disease can cause in humans. Okay, especially because of serious disease associated like Guillain-Barré syndrome and microcephaly that was observed in the recent infections. Okay, you can see here the map of Zika epidemic outbreaks in recent years. You see that it affected many countries in different continents. Okay, this disease spread all over the world in recent years. So we see that it's a very serious case to deal with. Okay, and here you can see the epidemic curve of Zika in Brazil in the year of 2016. Okay, you see that in the first months of that year, many cases were reported. Okay, we have in the peak around 23,000 cases reported a week, which for this kind of disease is a lot and causes a lot of concern. Okay, so in order to the authorities and the epidemic surveillance system be able to deal with this, it's very important to predict and describe the dynamics of these epidemics. In this sense, we want to contribute developing a model for a Zika epidemic in Brazil. Okay, we wish to verify from the quantitative and qualitative point of views the quality of this model. Okay, we wish to calibrate this model with real data in order to transform it in a tool that can be used in practice. Okay, and to compensate some possible deficiencies of the model caused by epistemic uncertainties in its construction, we're going to propose a novel approach here to enrich the model and improve its predictability. Okay, so here is the mathematical model structure. Okay, to describe the dynamics of Zika, we are going to concentrate our attention to populations, one population of humans and another population of mosquitoes, which is the vector of the disease. Okay, these two populations interact themselves in some way so that the disease is transmitted from the mosquito to the humans and from the humans to the mosquito. The group of humans is split in 4 compartments: susceptible, exposed, infectious, and recovered, while the mosquitoes, as live much less time than humans, are split only in 3 compartments: susceptible, exposed, and infectious. Okay, we just consider the natality and mortality for humans because in the interval of a year, the population doesn't change a lot. Okay, but for the mosquitoes, we consider because in the interval of a year, the population of mosquitoes is totally renewed many times. Okay, and an infected mosquito transmits the disease for a susceptible human, and an infectious human transmits to susceptible mosquitoes. Okay, when we translate this mechanism to mathematical language as a set of ordinary differential equations, this is the mathematical model we end up with, okay? A set of 8 ordinary differential equations with 7 parameters. We obtain these parameters from the literature, okay? We plug into the model, and with this, we're able to compute some quantities of interest that are useful for surveillance, okay? They are the cumulative number of infections and the new infections case per week. And when we simulate this model and compare with real data, what we observe in the first glance was this that you can see here. The predictions of the model and the data are completely different, okay? So for the set of parameters we use, the mathematical model is not representative. After first reflection, we arrive in the conclusion, well, maybe if the structure of the model is minimal, reasonable, the difference between predictions and observations could be due to the wrong values for the parameters. If maybe it's useful we try to discover a good set of parameters that promote a good agreement. And to do this, we need to solve an inverse problem. Okay, we need to calibrate the model, discover the set of parameters we should plug into the model to match the observations. And we attack this from an inverse perspective, and we calibrate the model with real data so that we could observe this. Okay, so the prediction here is much better. Okay, but we still can see, especially here around the peak, a mismatch in this region here. The model and the observations is still mismatched in this region and a little bit in the end of the dynamics. Okay, so despite the model predictions were improved with the calibration, they are not so accurate. And what we wish to do in this work is propose a novel way on how to improve these predictions, okay? And this will be done with the aid of something we call the discrepancy operator, okay? We have a baseline mathematical model, like this set of ordinary differential equations, okay? And we wish to add a correction for this model, and this correction is due by the discrepancy operator. And we choose this discrepancy operator proportional to the state of this dynamical system and to its first order time derivative, okay? And we identify this set of parameters kappa and lambda so that in order to promote a good agreement between this model and the observations, okay? These parameters were obtained with aid of Bayesian inference. And here you can see a comparison. The uncalibrated model in orange, 2 calibrated models with different set of parameters and constraints in blue and violet, okay? And you see the enriched, the improved model in red. You can see that its match with the data curve is much better than the other models, okay? And here you can see a propagation of uncertainty for this model, okay? In addition to improve the better nominal prediction of the model, with this approach, we also can construct a confidence band propagating uncertainties from the parameters to the model response, which may be able to compensate some kind of uncertainties. Let's see. Underreported data, it's very common in epidemics and unavoidable in some sense. It's impossible to note all the cases that happen. So one interesting question that arises in this setting is, can the confidence band from the uncertainty propagation compensate in some way the underreported data? We're going to try to answer these exploring 2 scenarios. One, which 90% of the cases are reported, and one where only 50% of the cases were reported, okay? This is a synthetic case we constructed to try to answer this question, okay? We constructed synthetic data and calibrated the model with the underreported data and compare now the model response with the supposedly total cases, okay? And we can see here that the envelope, the confidence band, in the case when we have only 10% of underreporting, is capable of to capture the real data, the real data behavior. And surprisingly, even with a higher underreporting rate of 50%, this envelope was able to capture too. So to conclude, we developed an epidemic model for Zika virus outbreak in Brazil. We calibrated this model and we enriched this model employing a discrepancy operator formalism, okay? And future directions, here we wish to investigate in deep the biological interpretation of the correction terms that we added to the model, okay? We can interpret simply those terms as control terms, okay? In some sense, we pilot the model to match the data, epidemic data curve, but in addition to this control perspective, a biological interpretation is interesting, and we are working on this now, okay? And a step ahead, try to infer this enriched model directly from data is very interesting direction to pursue, and is the following step, okay? We wish to acknowledge the discussion of this work with Professor Davi Santos from ITA in Brazil, the institutional support from Rio de Janeiro State University and University of Colorado Boulder, and the Brazilian funding agencies, okay? Acknowledge your attention. If you have any questions, I'll be happy to answer. Thank you.